I've started recording. I think we're ready to go. It's a little earlier than where we ended up last week. I just wanted to remind you of some of what we talked about, and then hopefully that'll lead into some new material for today. We spent most of our last meeting, most of last Thursday, talking about the connection between pointers and arrays. And we learned if we can get a pointer pointing to an array element, not necessarily even the first one, that we can use pointer operations to move around within that array, looking at values and even changing values. So we did a few little kind of toy problems like this, looking at how these move pointers around in an array. We learned a couple more things you can do with pointer arithmetic, including you can compare two pointers using all of the usual 6 relational operators. This, if we're willing to use syntax like this, it can give us some alternatives for how we traverse an array, how we iterate over an array or change what's in an array. And in some cases, this can let us write some code that's a little bit more efficient. We already looked at this example, but just, well, backing up. I stopped at this one because this is how you might access elements of an array using the normal array notation that you're accustomed to from Java. So here, when I want to get the ith element of an array, I can just use the square brackets to do that. But given access to pointers gives us potentially a bunch of other ways we can look around an array. And this is the one we ended on last time. Here, instead of using array notation, I'm going to use a few pointers to move around an array. Up at the top, before I even start traversing it, just like we did last time, I've made a 5-element array. I figure out how many elements it is, and I save that in length. And then I make a pointer that's pointing right off the end of the array. That's the one that I drew with this end arrow. And when I traverse the array, at least my plan for this solution is, that end marker will let me know when I'm done. I'm using pointer arithmetic here to figure out where that pointer needs to be. A evaluates to a pointer to the first element in the array. And then if you move 5 elements ahead, it should be a pointer pointing right past the end of the array. I probably mentioned this last time. You don't want to dereference that pointer. You can use it to compare with other pointers, but since it really points off the end of the array, you shouldn't be trying to look at or change the memory that it points to. But we can use it as an end marker like I'm doing here. So now, instead of traversing the array with array notation, I start out a pointer p. It starts out pointing at the first element. And then as I traverse the array, I bump p ahead using post increment on it. So every time I p++, it moves to the next element of the array. When I want to get that element, I dereference that pointer, so that gives me the value it's pointing at. In this picture, it would give me this, it'd give me a copy of this 9. And then as soon as p gets all the way up to end, as soon as it's no longer less than end, then I know I've traversed everything. So this is another way you can traverse arrays. And I think on one of the quizzes, and I think on sometimes on exams, I'll ask you to try to write code like this that traverses an array using pointer notation. Here's another way we could do it. I guess backing up, a disadvantage of this solution is you need this extra variable end just to keep up with where you stopped or where you're going to stop. Here's maybe a cheaper way to do it. Instead of, so same code up at the top, I make an array with 5 elements, but instead of traversing it going forward, I'm going to traverse it going backward. I start out p in this for loop. I started out pointing at the last element. So that I should be able to take the start of the array, add however big it is, and then back up by 1, and that should set p to point at the last element. And every time as I traverse the array, I just back p up. I move it to the previous element. The nice thing about this is if I'm going through the array backward, I can use the array itself to know when I've seen everything. So as long as p is no smaller than a, as long as I'm still pointing either the same place a is or somewhere later, then I know I'm still on the array. As soon as p backs up until it's an earlier address than a, then I know I've looked at every element of the array. I got one more example like this, and I'm just trying to give us some practice using this pointer notation for traversing arrays. Here is, it's my own version of a string length function. We learned probably last week about the strlen function. And I'm sure I mentioned the way it works is it just, you go to string and it just looks at every character in the string until it hits the null terminator. And then however far it had to go before it hit the null terminator, that would be the length of the string. And that function is not too hard to write. Here's an example of how we could write it ourselves. I just start out I pointing at the first character in an array, and I keep making I bigger until I hit the null terminator. And then when I do, I know I've looked at every character in the string, so I can just return that as the length. This first example up here is kind of like we did before. It's using array notation to look around that string. If we wanted to do it with more pointer syntax, that's what I'm trying to do over here. And at least the way I did it here, it does look a little bit shorter. I start out P pointing at the first character in the string, and then same as up above, I look at the character P is pointing at, and as long as it's non-null, as long as I haven't hit the null terminator, I keep moving P forward. Once I've done that, I should have a pointer P pointing to the end marker on the string, pointing to the null terminator. But how do I know how long the string is? There also I can use pointer arithmetic to figure that out. I can take the current location of P minus the start of the string, and that should evaluate to the integer length of the string, or really the number of elements between str and P. So I'll just compute that here at the bottom based on how far I got. We'll get more practice with this kind of thing, but those are the examples I brought for today. We've got one more topic, or a couple of related topics before we're done with lecture, officially lecture 10. Any questions before we move on? All right, we've now learned enough about pointers that we can make more sense out of literal strings. We've been kind of using literal strings all since the start of the semester, but we haven't really been able to explain what they are. But now that we know the connection between pointers and arrays, I think we can do a good job of that. This red thing up here is an example of a literal string. It's just a string inside double quotes. We know that a string is really stored in an array. A literal string like this evaluates to exactly what you would expect a character array to evaluate to. It evaluates if you just use a literal string like this as part of an expression. It evaluates to a char pointer, pointing at that A right there. Just like I started to say, just like you'd expect for any array. Evaluating the array, treating it as part of an expression, gives you a pointer to its first element. So this, a literal string evaluates to a char pointer. When you use a literal string, you're telling the compiler to go find some room in memory, store that sequence of characters as an array with an end marker with the null terminator at the end. And then whenever you use a string like this, like I said, it evaluates to a char pointer, pointing at the first thing in that string. Well, since you can index off of pointers just like they were arrays, it looks a little goofy, but the syntax down here at the bottom works just fine. If you say, give me a literal string ABC123, and then take the char pointer it evaluates to and index 2 elements past the start, this would give you this C right here. I'm making a string, and then I'm looking up element number 2 in the string. There are really a couple of ways to make strings, and I want to, and they're similar. A lot of the same syntax works either way, but they are implemented differently, and it's worthwhile to understand the difference. That's kind of what I'm showing here. I'm making a string up here as a character array, and I'm setting it to ABC123, and it'll put a null terminator at the end. Here I'm using the array initialization syntax. So when I make this str1, I'm really getting a 7-element character array. 7 because I've got each of these 6 characters here, and one more null terminator. If you make a string like this, I got a picture down here at the bottom that shows how I think about it. I'm making a new array, and I'm just initializing it with that sequence of characters. You could also use a literal string like this. In this second example, I'm not really making an array. I'm making a pointer to a char, and I'm making it point to this literal string. So str2, when you make a string like this, I think of that as giving you something more like this in memory. str2 is just a pointer, and you initialized it so it points to this literal string allocated somewhere in memory. One difference that you'll usually see between these two types of strings, well, I guess if you asked size of how big they are, this top one, size of, would say, oh, it's the size of the entire array. It's 7 bytes in size here. Whereas in the second example, it would just tell you the size of this pointer, because str2 is a pointer. It's a char pointer. It's just one that we set up to point to a literal string in memory. Like it says over here on the right, one other difference is usually a literal string like this is not going to be modifiable. When the compiler allocates space for that, it puts it in a region of memory that's read-only. So in this top example, you're going to get a real array that you can change if you want to. You can change what string is in it. But in the second example, if you follow this pointer and try to modify one of these characters, it's probably going to crash your program. That depends somewhat on compiler settings and what platform you're on. But on the common platform, that's what you're going to see. Literal strings like this are allocated in read-only memory. Here I'm showing really two ways to make things that kind of work like character arrays. I made a character array here and I copied this ABC123 into it. And the second example, I just made a pointer to a character, but then I can use that pointer to index into this literal string. Like I said, I just can't change the characters in that string. Strings have a special syntax. That's what we're using here that makes it easy to initialize strings with particular character array values. You can do the same trick with any type of array. It's just the syntax is a little bit bulkier. You could make an array of integers. And this top example is kind of analogous to what I just did with a string. I'm making an array. I'm using initialization syntax to get the compiler to put these 4 elements in the array. So this makes a 4-element array. If this was part of a function, if this was inside a function, then it's being allocated on the stack. Whereas the second syntax is backing up. It's more like what I'm doing here on the bottom. I want to make an array, but I just want to get a pointer to that array. So I made an int pointer, and I can use, once I've made it point to an array, I can use it to index into that array just like any other array. This syntax over here on the right, this is the first time we're seeing this. That is a way of making an array and getting the compiler to allocate this array. In this case, it would be stack allocated, getting it to put the 4 elements that I asked for in the array. And this syntax evaluates to a int pointer. If I said I want an array of these 4 values, this thing over here in parentheses that looks kind of like a typecast, that's telling the compiler that you want it to allocate this sequence of 4 values as an array of integers. And then, like I said, this whole thing evaluates to an int pointer. Kind of like back here. We said, well, this literal string evaluates to a char pointer. Here, if you make an array like this, it evaluates to an int pointer. We'll spend a little bit more time on the syntax. I wanted to go ahead and introduce it because I'm trying to show how to do the same kind of thing with a character array or with a integer array. Like I said, we'll revisit this and you'll get another chance to practice with that syntax. That gets us caught up with the end of lecture 10. We caught up a lot last time. I probably talked a little faster than I normally do. And today we might get caught up with the end of lecture 11. Before we start on lecture 11, any questions? All right. Today, we get to learn about a new memory region. And this is, I mentioned a couple of times when we spent time learning about pointers, I've tried to tell you, well, here's what pointers are good for. We talked about how if you're opening a file, you have to use pointers. If you're doing pass by reference, that's usually done as pass by address. This is a big topic that requires the use of pointers. Pointers will let us allocate memory in a region that we'll call heap memory. And this will let us do a lot of things that we couldn't do if we only had access to stacked memory and statically allocated memory. So allocating memory on the heap is usually called dynamic memory allocation. That lets your program, as it's running, it can decide when it needs more memory. And part of the C standard library will allocate memory for, or can go find that memory and give back a pointer to it. Before we can learn the API, before we can learn how to do dynamically allocated memory, heap allocated memory, we need to learn about one other kind of pointer, and that's the void pointer. Void is a weird type because we don't get a whole lot of use out of it. In Java, I think maybe the only thing you do with the void type is you define functions that don't return anything. You define void functions. You can still do that in C, of course, but we do get a little bit more use out of void in C by making void pointers. So like my slide tries to show, you can't make a variable of type void. The compiler, you wouldn't be able to store anything in it. Void is a type that doesn't have any values in it. So you can't do this top example. You can't make a variable of type void, but you can make a void pointer. And here's how you declare it. Just like you'd expect, I want a pointer named VPTR that is of type pointer to void. What are void pointers good for? Well, in C, that is the mechanism for having what you might think of as a generic pointer. For most pointer types, the compiler tries to make sure that you can only make them point to the right type. So for instance, if you have an int pointer, you can make it point to an int, but not the compiler will complain if you try to make it point to a float. If you have a double pointer, you can make it point to a double. Void pointers are a mechanism for having a generic pointer. If you make a void pointer, you can make it point to anything you want in memory, and the compiler won't complain about that. So think of a void pointer as a mechanism, like I've said a couple of times, for holding generic pointers, pointers that you could use to point to anything. Here's how we do it. So we're using the void pointer I declared up here. I made a float variable. I got its address, and I can store that in the void pointer. It's just that void pointer is holding the address of a float at this point. I could change my mind later, since this VPTR can hold the address of anything. If I later decide I want to make a long and get the address of that long, the compiler will let me store that in a void pointer. Since void pointers are generic, they could point to anything. It means if you're going to use them, you have to turn them into a more specific type before you use them. So backing up, the last thing I did on this slide is I took the address of a long and I stored it in this void pointer. If you wanted to print out the long that points to, you can't do it like I'm showing up here at the top. You can't dereference a void pointer and then use that without casting it to something more specific. So since void pointers are a mechanism for having generic pointers, if you want to use whatever they point to, you have to help the compiler out by letting it know what type it really points to. And that's what I'm showing on this next slide. So here I take a same void pointer we've been playing with. Let's pretend that I know that it really holds the address of a long. If I want to look at the long that it points to, I can take that void pointer and assign it to a more specific pointer type. So I take whatever's in that void pointer and I store it in this pointer to long variable that I made here. And then I can dereference that. So I can follow the long pointer and see the long value that that it points to. The point I'm trying to make is without this cast, without going to a more specific type, the compiler won't let you look at what a void pointer points to. I'm about to make the last point on this slide. Since the compiler uses void pointers as a generic pointer type, it doesn't even require typecasts when you move back and forth between void pointers and other pointer types. That's what I'm showing up here. I took whatever a void pointer points to and I assigned it to this long pointer. Well, I'm going from a more generic type to a more specific one, but in this case, the compiler doesn't require a typecast. You can put a typecast, and that might help the compiler detect some errors. So you'll often see me using a typecast when I get a void pointer, casting it to a more specific type. The language doesn't require that. I'm just, part of it is coming from C++. That is, you do have to do the typecast there. So when I'm writing my C code, I usually try to write it so it would also work with a C++ compiler. All right, that was a long trip talking about void pointers. The real reason I introduced them is to talk about this third region of memory that we haven't used until today. I drew a pretend picture of how you can think of your memory. You know, there's a static region of memory and any global variables get allocated there. You know, there's a stack region of memory and local variables inside a function get allocated there. And today we're going to be talking about this new region called heap memory. What is the difference? Well, you already know the static region of memory. Anything that's allocated there gets allocated when your program starts up, before it even starts running. You know that variables in the stack region of memory get automatically created whenever you call a function that uses that variable, and they automatically go away when you leave that function. Heap memory gives you control over when space is allocated and how long it stays around. So we'll see in a moment, there are functions you can call where you ask for more heap memory, and then you can use that memory for as long as you want. The runtime environment will set aside that memory for you until you say that you're done with it. And like I said at the start of lecture, usually when we're using this region of memory, the heap memory, people will call that dynamic memory allocation. So how do we use this heap region of memory that we haven't talked about until today? There are functions in the standard library for asking for more heap memory and for saying when you're done with it. So we just need to learn how to use those functions. If you want to use these functions, if you want to use dynamically allocated memory, the declaration for those functions is in standardlib.h. So one of the headers that we've been using all semester long. And this function down here, malloc, is probably the main function you will use for asking for heap storage. It's pretty simple. You go to malloc and you say how much memory you need. And you pass that in as a parameter. So if you need 100 bytes of memory, you could pass in 100 as the parameter. If you need 1,000,000 bytes of memory, that's how much you ask for. It returns a pointer, so like my picture tries to show down here, the runtime environment, the C standard library is keeping up with, all the time it's keeping up with where the heap is, what chunks of memory in the heap are in use, and which chunks are free. So when you go to malloc, and you say, I need 100 bytes of heap memory, it finds, if it can, it finds a region of memory that's at least as big as what you asked for, and it returns a pointer to that. So it tells you where it found that memory. And this is why we started talking about void pointer a moment ago. Notice it returns it using that generic pointer type that I talked about a moment ago. So this is the first part of the mechanism that we might use for dynamic memory allocation. But how would you actually use it? What would you actually do with it? Well, that's one reason we took a side trip talking about arrays and pointers. Because one of the main things you might want to go to malloc to get space for is a big array. If you know how many elements you have to store, you can compute how many bytes you need, how much memory you need to store an array of that type. And that's what I'm trying to show in this example. You can allocate other things besides arrays. you can allocate space for anything, but arrays are one of the things that we use most often when we go to malloc asking for space. So this example in the middle of my slide, I'm showing how to allocate space for a 1,000 element array of ints. How much memory do I need for that? Well, I can go to the compiler and say, how big is an int? And on the common platform, that's going to be 4 bytes. And then if I know I need space for 1,000 of those, one after another in memory, I can just do a little bit of math to figure out, oh, I need 4 times 1,000 elements. And then if malloc can find space for that, it'll return a pointer to that. And I think here's maybe the other interesting part of this example. I take that pointer and I put it in an int pointer. The reason for that is we just learned that if I've got a pointer to an int, I can use that almost exactly like an array. So once I've allocated space for 1,000 elements of size int, if I hold that, the pointer I get back, if I hold that in an int pointer, then I can index into that array just like any other array. Let me quickly say, why do I need to do this? Well, like I said, for other regions of memory, like stack memory, stuff on the stack goes away whenever you return from the function that declared that thing. Whereas this memory, the memory you get back from malloc, it's not going to go away until you say you're done with it. I've got one more example here. If you think of this top example as making room for a 1,000 element array of ints, this bottom one makes room to copy a string. If you had a string str and you wanted to make a copy of it in memory, maybe you wanted to copy it from a local variable to memory that was going to be around for as long as you wanted, you can go to malloc and you just have to say how many bytes you need to hold that string. And if I just wanted to copy an existing string, I could go to stringlen and say how long is that string. That's going to count everything except the null terminator at the end. So I add one more byte to hold the null terminator, and then malloc will return a pointer to memory that's at least big enough to hold a copy of this string that I'm trying to copy. Questions? So we're going to sneak up on a few different examples of these calls. I'm just trying to show you what the mechanism is. I've said a couple of times, the nice thing about heap memory is it stays around. It's going to be reserved for whatever you're doing with it until you say that you're done with it. And here's how you say that you're done with it. If you malloc space with malloc, if you allocate heap memory using the malloc call, here's how you give that memory back. There's a function called free, and you give it a pointer that you previously got from malloc. So you only want, if you're using free, you only want to free things that are pointers that you got from malloc. And this gives the memory back to the C standard library, like my picture tries to show. If you've got a pointer that points to some memory that you malloced, and now you know that you don't need it anymore, you can call free, give it that same pointer, and then that memory is given back to the heap. It probably will get used for something else if you later call malloc and ask for more heap memory. So this is typical. Like I said, we're kind of sneaking up on how you would normally use heap memory. And here I'm just showing off a more typical example. So let's say you wanted to make an array on the heap and you wanted to use it to store some stuff. You could go to malloc, and this is the same kind of call we had before. Ask for how much memory you need. So you can think of this as space for a 1,000 element array of ints. And then, like I made the point before, if you store that result in a int pointer, then you can index off of that int pointer just like any other array. And you can, and I'm showing pretend examples of copying things around using this array to store a bunch of stuff. And then when you know you're done with that array, eventually you're going to want to call free on that to give that memory back to the heap. This is how you might typically use this. I guess here, it's almost the same as what we just looked at. The difference here is instead of just having tiny little code fragments, I'm showing how you could traverse the array you just allocated. So I allocate space for a 20 element array of doubles. I hold that in a double pointer. And then if I want to iterate over that array, I can look up element 0 through 19. I can store things there. I can index into that array and then use that value. Here I'm just printing out those values. And then when I'm done, it's up to me to remember to free that memory. So this is maybe a more realistic example of how you would use malloc. Here is an example of why you might want to use malloc. Before I talk through this example, any questions? All right, I hope people are still there. So here I've got a function that's doing something that I couldn't really do, or I couldn't do a good job of this without having access to heap memory. This function, I called it read list. The idea is you call it and it will read any number of values, any number of ints from standard input, and it'll return them to you by returning a pointer to some dynamically allocated memory. This is what I was talking about before. Without heap memory, I think it'd be a lot harder to write this function, because if inside the function you stored all those values in a stack variable, that variable goes away as soon as the function returns. This, with heap memory, I can hang on to that memory until I know that I'm done with it. So the job, or the idea is you call this function, you give it, well, it's going to read in a list of integers and it's going to store it in a dynamically allocated chunk of memory that we're going to use as an array. It's got a parameter here that I called length. I made that parameter an int pointer, but I'm really thinking of it as a pass by reference parameter. So I call this function, I give it a length, I give it the address of a length variable. And then when the function returns, I can look at that variable to see how big the list was. Again, I pass it by address because I want the function to be able to modify that so that when it returns, the caller can tell how many values got read in. Over here, the return value of the function, that's going to be my list of values. I know they're the same type, but I'm using them differently. That's one reason I'm trying to make a big deal out of this. This parameter, you can think of that as one integer that I'm going to pass by address to this function. And the return value, you can think of that as a whole array of integers. I'm just returning a pointer to the start. This is a thing that is a little unfortunate in the design of C. We use pointers to pass single values by address, and we use pointers to pass around whole arrays by their starting address. And there's not really anything in the type system of the language that makes that distinction. So if I was writing this code with someone else, I would have to depend on something like comments to help explain all that. Is just one integer that's passed by address, and the return value is a whole array that's returned by returning its starting address. All right, enough stalling. Let's talk about what goes on in this function. The first thing I do is I'm going to count on the user telling me how many values they're about to type in. So if they're going to type in 100 values, they need to start by saying, I'm going to give you 100 values. So I'm reading whatever integer they type in, and I'm storing it in this len field. Notice I don't have an ampersand there because I'm already counting on len being the address of an int. The reason I put the ampersand in front of it in the first place is to get the address of an int. But if the caller did the right job giving me the address of wherever they want the length stored, it's already the address of an int. I can just call scanf and give it a copy of that. So if the scanf is successful, now I know how many values I want to store. I go to malloc and say, however big an int is, I want len times that many values. So if the user just said, I'm going to give you 20 input integers, I'm going to allocate space for 20 integers. Notice here I'm doing the dereference operator, and also down here, because if len is a pointer to an int, every time I want to look at the int it points to, I need to dereference it. So if malloc is successful, I get back a pointer to an int. I get back an array of ints via its starting address. I save that in an int pointer, and then I can traverse that array just like any other array. And here I'm just reading over and over. I'm trying to read an int into the ith element of that array. Here, I'm showing off pointer arithmetic. If list is an array, you could have put square brackets after it and then put an I in there and inside the square brackets and put an ampersand in front. But this does the same thing. Remember, pointer arithmetic, if you give it a pointer and then you add an integer to that pointer, you get the address of the ith element of that array. Now, scanf wants the address of an int if I'm telling it to read an int. So just using pointer arithmetic here is an easy way to go get the address of the ith element in the array. And then if all this was successful, once we're done, we return the dynamically allocated list. So the caller is going to get back a pointer to an int. They can look in their len parameter that they passed in to know how big that array is. Here's, so this is the function we've been talking about. This is client code, or this is how you might normally use this function. So if you want to call read list, you're going to need space to know how big the list is. So I made an int for that, and I pass its address as a parameter to read list. And then it's going to return back an int pointer, which is my way of looking at the array that it allocated. So I save that in an int pointer, and then from the caller, even though that function is done, the array it read in is stored in heap memory. So I can use that as long as I want to, but then when I'm done using it, somebody's got to be responsible for freeing that memory. So before I go do anything else, I free the space that I got back from the function. So backing up, here's where the space gets allocated inside this function. And then once I know I'm done using it, I free that memory. I've said a couple of things that I hadn't explained yet. I said things like, if malloc can find the memory you want, it returns a pointer to it. What if it can't? Well, I skipped this detail earlier, but that's one of the jobs of a null pointer. If you call malloc and it can't allocate the block of memory that you asked for, it lets you know that by returning a null pointer rather than a pointer that's defined. So you can check the return value you get from malloc as if it was a truth value. And if it was able to successfully allocate space, you'll get back a non-null pointer. This is important to remember. Just like stack memory, heap memory, you should treat it as if it's uninitialized. When you allocate space on the heap, it could contain garbage. The reason is the same as with stack memory. As your program runs, the standard library reuses the same memory over and over again for dynamically allocated storage. So when you allocate a big block of dynamically allocated memory using malloc, it's going to contain whatever used to be there the last time your program was using that memory. So it means you shouldn't count on it being full of zeros or any particular value, unless you write your own code to fill it with zeros. That stuff at the bottom we've already talked about. I'm just reminding you of that size T type, and that's the type for the size of things in memory. And you can see that's the parameter type that malloc is expecting. If we're using heap memory, it means we're having to use pointers. We're keeping up with that heap memory. When we go to malloc and say I need some memory, it gives us back a pointer to that. So to use that memory, we've got to be able to use pointers. So that's one reason we learned pointers before we started talking about malloc. Just like any other application where you're using pointers, it's easy to accidentally make some mistakes with pointers. If you accidentally use an uninitialized pointer, then you're asking your program to access who knows what location in memory, and that could crash your program. So all of the hazards we normally think about with using pointers, we'll need to keep those in mind when we're using dynamically allocated memory. There are some new mistakes that we can make that we didn't have to worry about until we started using dynamically allocated memory. And one of the most common things to mess up, one of the things that you need to keep in mind is whenever you allocate dynamically allocated memory, you should have a plan for when you're going to free that memory. Kind of like we just saw in that code, I had one function that allocated some space with malloc, and then the caller of that function took the responsibility to free that. If you forget to free dynamically allocated memory, like if you've got a program and it just, as it runs, it needs more and more dynamically allocated memory, but you never bother to free that memory even when you're done using it, we call that a memory leak. And the problem with that is if you keep allocating memory, but you never free it, even when you're done using it, you never free it, then eventually you're going to run out of memory. And I mentioned on a previous slide, if malloc can't allocate the memory that you ask for, it's going to return a null to let you know that you can't have that memory. And this is the kind of thing that could cause that to happen. If your program is gradually leaking memory or allocating space, but you never bother to free it, then eventually you're going to run out. So a memory leak is when you allocate space and you forget to free it. We're going to pretend that just to do a good job writing programs, we're going to pretend it's our job to free any memory that we allocate before returning. Or I guess more accurately, if our program exits successfully, so it doesn't run into errors when we run it, we'll generally say, well, part of exiting successfully means you're going to free all the dynamically allocated memory that you've asked for. So forgetting to free dynamically allocated memory is a potential error. Accidentally using memory that you've already freed is also bad. In fact, this is probably worse. We've got a name for that. A dangling pointer is when you've got a pointer and it points to, like my picture tries to show, it points to a chunk of memory in the heap, memory that you allocated, but you've since freed that memory. You said that you don't need it anymore. What happens if you accidentally use this pointer? Well, the malloc can't stop you from using that pointer. But if you accidentally use a pointer into memory that's no longer yours, that you gave back to malloc, that can crash your program. It's called, like I just said, it's called a dangling pointer. And this is sometimes a particularly tricky error to debug, because if you accidentally access memory that you shouldn't access, it may not crash your program, and it may not crash it right away. It might accidentally write something into heap memory that messes up the heap data structure, but it may not mess it up in a way that's immediately noticeable. It might cause your program to crash at some point in the future when you try to use malloc again. So those errors that that break your code but not right away, that kind of mess something up, that breaks your program later, I find those to be particularly challenging to debug. Accidentally accessing memory that you've freed can introduce a bunch of potential flaws in your program. That's kind of what I've been saying. Even potentially security flaws. If you allocate memory and then some other piece of code is able to find that memory, it might be able to get access to sensitive information that maybe you didn't trust that other piece of code to be able to access. So we're kind of covering potential errors when you're using dynamically allocated memory. One mistake, honestly, I don't think this mistake is that common, but it would be a mistake. If you allocate space with malloc, you're expected to free that space eventually, but only once. Down here, we're showing accidentally doing a double free of memory. Here I'm malloc space, and then I'm pretending to free it, and that's fine. But if I accidentally take that same pointer and try to free that memory again, that's probably gonna mess up malloc. Also, up here at the top, you're only supposed to free memory that was allocated with malloc. If you've got a stack variable like this one, this is that same array syntax we were looking at a moment ago. If you have a pointer to stack memory, you shouldn't try to get free to put that back in the heap because that wasn't part of heap storage. So you should only call free giving it pointers that you at some point got from malloc. Um, just like accidentally accessing a dangling pointer, accidentally trying to free things that you didn't malloc, or freeing things more than once can corrupt your free memory heap. And like I tried to say, that can crash your program, maybe not right away, but maybe a little bit later. In Java, we have been, for years, we've been using a region of memory that is pretty much the same idea as the heap. I didn't describe it this way, but whenever you use the new operator in Java, either to allocate a new object or to allocate a new array, you're kind of doing the same thing malloc does. You're asking for memory that the compiler will, or the runtime environment will keep around until you're done using it. Well, in C, we have to help out the runtime environment. We have to call free to let it know when we don't need a particular chunk of heap memory anymore. As you know, in Java, Java makes this a little easier for the programmer by always doing garbage collection. So whenever you go to Java and you call the new operator and you get back some allocated memory, it will pay attention to when you're using it. And as soon as you can't, well, once you can't get to that memory anymore, it'll automatically reintegrate it in its pool of free memory. And then that could be available for something else in the future. C doesn't do garbage collection for us, so we have to think about freeing our own memory when we're done with it. We'll see maybe at the end of this lecture, that can have some performance benefits for C program. It can be a lot faster because it doesn't have to be running garbage collection all the time, but it is one more thing that the programmer has to keep up with. I've tried to make the point that for some things, malloc and free can let you do some things that would be hard to do without those regions of memory. But I would say don't overuse dynamically allocated memory. I think compared to statically allocated memory and stack memory, those two regions of memory are much easier to use. Stack variables, I don't have to worry about freeing them. They automatically go away when I return from a function. Statically allocated variables, the compiler takes care of allocating those and initializing them before my code even starts running. They can be a lot faster than dynamically allocated memory. So I would say continue to use those two regions of memory wherever you can, but there are going to be some places where you have to use heap allocated memory. So use it when you have to, but don't forget about those other regions of memory that, like I've said, are probably a little bit easier to work with. I've got another example here. It's kind of like the list that we looked at. I'm trying to write a program that does something, or a little fragment of code that does something that would be hard to do without heap memory. Let me tell you what my program tries to do, and we'll talk about what it does wrong. This is our first attempt at writing this program, and it's got a bug in it. Let's try and talk about what it's supposed to do, and then we'll talk about what goes wrong and how we can fix that using heap memory. This is a function. You call it, and it tries to read a list of words from standard input. So when you call it, you give it an array of char pointers. So it's going to make each of those point to a word. You know how big your array is before you call it. So maybe you've got room for 100 words, maybe you've got room for 50 words. That's what this capacity field is supposed to be. Before you call the function, you give me an array of pointers, one for each word, and you tell me how big the array is. Inside the function, I'm going to read as many words as I can until I either run out of capacity or I hit something that doesn't parse as a word. And then I'll return to you the number of words I successfully read. So let's talk through what this program is trying to do. So I just talked through the parameters and the return value. Inside the function, I'm going to count words as I read them. So I start out my count at 0. I have space for up to a 99 character word. So think of this str as scratch space. Whenever I read a word, I try to put it in this str variable. And then, like I said, as long as I haven't run out of capacity, I haven't used all the slots in your array, And if I go try to read a word of up to 99 characters and store it here, as long as that's succeeding, as long as scanf is saying you successfully read one word, I'm going to store that word in my array. I'm going to count it. And then once I'm done, I'm eventually going to return this count. So at least that's the plan for what this program is supposed to do. It probably doesn't work the way you want it to. And I wanted to make that point. To help with this, I made a little picture that shows what this program or what this function is really going to do. So you call this function, you give it an array of pointers, and your plan is each of those pointers is going to point to a word. This line of code right here, my array of pointers, my current element of it, I want that to hold the address of the string I just read. Well, in Java, this kind of thing would work because strings are always heap allocated. They're objects, so they get allocated, just like stuff with the new operator. The problem here, though, is in this C program, every time we read a word, we're putting it in this 100-element string array. And that string array is just getting reused every time we go around this loop. So when I read a string here, it goes in that string array. When I come back around again and read another string, it goes in that same array. Now, after I've read a word, I fill in the next pointer in my words array, but for every one of those pointers, I'm making them point at the same string array. And I think of this picture as showing what that's doing. When you return from this function, every time you set up one of these pointers, you made it point to the same place. So however many words you read, you're going to have a pointer, each of it pointing to the same array. Whatever's in that array is just going to be the last word you happened to read. Since we were just on this line, we're overriding that array every time we try to read a word. And all of these pointers are pointing to this little 100-element array, which is a stack variable. And it's going to go away as soon as this function returns. So this function, it's got some good ideas in it, but the fact that every pointer we put in this array is pointing at the same place, and that the place it's pointing to isn't even going to exist after the function returns. I think we can fix that. I just think it's going to require a little bit of dynamically allocated memory. Instead of having all of these pointers point to the same place, whenever I read a word, I want to make a copy of it. At least that seems like it could fix this problem. Instead of having all of those pointers point to the same array, every time I read a word, I'm going to copy it into some dynamically allocated memory. I'll fill in the next pointer to point to that new piece of dynamically allocated memory. And then every one of these pointers is really pointing to its own string in memory. What would it take to do this? Well, it's almost the same code. I just have to do a little bit more work here. Same parameters, same return value. I'm going to count strings as I read them. I've got a 100-element array to use as scratch face, as long as I'm successfully reading strings. And here's the part that I changed. Instead of just saving a pointer, backing up a slide, instead of just saving a pointer to this stack array, I'm going to dynamically allocate space to hold a copy of the word that I just read. Kind of like we looked at earlier, I can call string length to find out how big the word I just read is. I need one more byte to hold a copy of the null terminator. So I'll add in one extra byte, I'll malloc that space, and then I'll make the next pointer in my words array point to that dynamically allocated space I just got. That space is uninitialized until I put something in it. So once I've allocated enough space for the next word, I'll copy the word I just read into the space I just allocated. So notice I'm using the same place where I just stored the pointer I got back from malloc. And remember, we saw string length about a week ago. It copies from source to destination. So this should overwrite each of these malloc pieces of memory with the word I just read. And when I return from this function, each of those pointers is pointing to its own little chunk of dynamically allocated memory. Now, somebody's got to be responsible for freeing that memory. Here inside this function, I allocate space for each copy of a word that I need. Once this function returns, somebody, probably the caller, needs to be responsible for eventually freeing that memory. We've mostly been playing with little examples so far. The next thing I want to show is one of the most common things that you might do with dynamically allocated memory, and that is build a data structure that grows as needed. Instead of having to allocate all your space at once, it's handy to have a data structure where you can add a little bit of stuff to it. And then if you need more room, you can make it a little bit bigger, and you can make it a little bit bigger. Before we start talking about that, are there any questions about the examples we've been doing? All right, I'm not hearing any questions. So let's build a resizable array. This is probably something you did in your 216 class, and we're going to be using the same ideas to build an array, a simple data structure that'll start out with room for a small number of items. And then as we keep putting more stuff in the array, we'll write code to go allocate more and larger space to hold more things as we put them in the array. This trick is often called a resizable array. If we want to be able to handle arbitrary amounts of data, we might have to try to figure out how to write, hopefully, a little bit of simple code that can go in and enlarge a dynamically allocated array whenever we run out of room. So, like I said, you've probably done this in your 216 class. I've got some pictures that try to show how this is going to work. To build a resizable array, we generally need three things. We need a pointer to an array. I'm going to call that list. It's going to be a pointer to dynamically allocated memory, and that's the thing that I'm going to grow as needed. Initially, I'll malloc a small amount of space for that array, and then as I put more and more things in it, I might have to go back and ask for additional memory for that array. So I've got a list. It's going to be a pointer to some dynamically allocated memory. I need to know how many things are in my list. As I put items in it, I need to count the number of items I put in it so that I can know when I'm going to run out of space. So I'm going to have a variable called len, which I think of as the length of the array or how much stuff is in it now. And I'm going to need one more variable for keeping up with how big the array is. I'll call that capacity, and that's so I can tell when I've used up all my space. Once I fill up everything in capacity, I have to go and allocate a larger chunk of memory to hold more items. So between length and capacity, that'll let us keep up with how full the array is now, and it'll let us detect when we run out of room. So initially, I'll allocate a small array. I think in my example, I've got a 5-element array. And that means I can start putting things in the array until I've used up all of those 5 spaces. So every time I put an item in, I'll increase len to keep up with the fact that I just put one more item in the array. And it'll also tell me where the next free space is in the array, because I'll start filling it from the front to the back. Once I've used up all of my capacity, once len reaches capacity, so if you've got room for 5 items, and there are already 5 items in the array, then you're not going to be able to put more items in. But this is where I'm going to do that resizable array trick that, like I said, you've probably done in your 216 class. When I'm out of space, I'm going to go back to malloc and I'm going to ask for an even larger array with more room. Well, this new larger array I got, if it's coming out of heap memory, it's a bunch of uninitialized bytes of memory. If I want to start using this new bigger array, I'm going to have to copy over everything that was in my smaller array. So after I've gone to malloc and asked for more space, I'll copy all my stuff over. And now once I've copied it, I don't need the smaller array anymore. So here's when I know I can free that array. Once I've copied everything over, I call free and I give it back the old smaller array I was using. And then from this point on, that new bigger array, that's my list. So next I'll take my list pointer and make it point to my new larger array with more capacity. And now, at least for the time being, I've got space to put plenty more items. And then if I run out of all that space, I can do this same trick again. I can go ask for an even larger array and then start using that space. I've got 4 example programs for showing this. They're all almost the same. So they're just slight refinements on the idea. We're going to start out looking at this one. Instead of looking at it here in the slides, though, I thought we would try to write this program. I got a terminal window that's logged in on one of the common platform machines. And I've got the code we were just looking at in the slides is this resizable.c program. It is kind of like that read list program that we looked at before, where it would read how many values you want the user's going to enter, and then it'll read each of those values. But this one's a little bit smarter because you don't have to tell it in advance how many items are going to be in your list. It is going to use this resizable array trick to allocate a smallish array, and then when we run out of room, it'll go back and get a bigger array and a bigger array. Let's take a quick look down at main to see how it gets used. The real function, the one that we care about, is going to be this one called read list up here. Kind of like the one we saw earlier in class. You give it the address of an int. So this is where it's going to store how many values it read. So what's the length of the list? And it gives back a pointer to an int. So it gives back the array of values that it read by giving back an int pointer. And then before we exit, we print out the list of values we just read. I print it out backward just to show that I really read it into an array. And then before I'm done, to make sure I don't leak that memory, if this function read list allocated that space dynamically, then I'm going to be the one responsible for freeing it. So the last thing main does is free that memory. All right, let's look at the read list function. So we already talked about the parameters. You give me the address of an integer length, and I'll give back a pointer to a dynamically allocated array of stuff that I read. These top 3 things, and you can see I've tried to comment this code to help illustrate what we're talking about. These top 3 fields are the ones we were just talking about. I'll start out with an initial capacity. I'll have room for 5 items on my list. Initially, there won't be any items on my list, so I start that out at 0. I want my list to be able to grow as I need more and more space, so I'll allocate it out of heap memory. I go to malloc, and I say, however big an int is, I need space for 5 of those. And until I run out of room, this is going to be my list, this pointer. Once I have an initial list, I'm just going to keep trying to read numbers from standard input. So I'm reading them, storing them in this temporary variable. And then before I put them in the list, I worry about whether I've run out of capacity or not. Now in our slides, this code is already written, but instead of just talking through it, I thought we'd try writing it together so we can see how to do this in C. And that'll give me a chance, hopefully, to explain it. All right, so as we talk about how to build a resizable array, so every time I read a value, I'm going to store it in the next spot of my list. And then at the bottom, when I return that dynamically allocated list. The part of code I just deleted is the part that says, you better make sure that you have enough capacity in your list. So before I can store the next item, I need to worry about, have I run out of capacity? So that sounds like a good job for if. If you've used up all your capacity. So if len is greater than or equal, it should never really be greater than capacity, but it's just as easy to write it like this. So if len gets all the way up to capacity, if you've run out of space, then you're going to have to resize the array. So that's what's going to go inside these curly brackets. First, it seems like you want to decide how much bigger the array needs to be. Like I said, you've done this probably in your 216 class, and you're probably accustomed to every time you run out of capacity, it's common to double the capacity. I'm not going to do that here. I'm going to do it stupidly by just making capacity a little bit bigger. It'll be easy to go back and fix that later, but in coding it that way first, we'll at least get to talk about why that's a bad idea. So if I need more capacity, I'm going to make capacity just a little bit bigger, room for one more item. All right, so I increased the capacity. At least I decided that I'm going to need more capacity. So now it seems like I need to go to malloc and ask it for a bigger array. So we'll go to malloc and we'll say, now I need capacity, my new slightly larger capacity, times however big an int is. What do I want to do with that? Well, we already said malloc's going to give us back a pointer. I better not store it on top of this list pointer, because if I did, I would lose my old list. I wouldn't have any way of getting to that, and I would have just leaked the memory for that. So I'm going to need a new temporary variable. And I'll set that to whatever pointer I get back from malloc. So this is my new slightly larger list. I don't need this typecast. I mentioned that since malloc returns void pointer, you can assign it to any other pointer type without a cast. But I usually put a cast in here, and then whatever I'm writing will compile just fine on languages like C++, where its type system is a little bit trickier, or is a little bit stricter. All right, so I got a new bigger list. Seems like the next thing I want to do is copy everything over. So I had, let's say, 5 items on my old list. I need to copy those 5 items over to my new bigger list. That's one of those things where we don't have a whole lot of programming language syntax that works with a whole array at once. So if we want to copy an array, we're probably going to have to, at least for now, we're going to have to write a little loop of code to do that. So I'll just loop over all the items on my list. And now I've got a loop that iterates one iteration for every item. And then I'll just copy each iteration. I'll copy over to new list at I gets list at I. All right, so now I think I'm almost done. I've increased the capacity. I went out to malloc and got an even bigger chunk of heap memory. I copied all my stuff over. I guess I don't need the old list anymore. And this is my chance to free that memory because I have a new larger list. So free the old list. And then now I think I'm almost done. Now the list I just made, new list, that's going to be the list that I use henceforth. So list is new list. I think we'll give this a try. Any questions before I try compiling it and seeing how it works? All right. I think I've got a GCC. Yeah. So I compiled it earlier, so I'll just reuse that GCC line. We didn't make any syntax errors because it compiled cleanly. Let's take a look at. I've got a couple of input files we can try this on. So instead of typing in numbers myself, I'm going to read them from this file. This first one, I just put in 25 random numbers. You can see the first one on my list is this 97. The reason I mention that is we can use that to check and see if it looks like it did the right thing. It's going to print out this list of numbers backward after it's read it in. So if that 97 shows up at the end, then it probably did the right thing. So resizable, and then let's have it read from hard input. It'll happen quickly. Yeah, there's that 97. That array, the resizable array that we made, started out with just 25 with 5 elements in it. And then as we ran out of space, we grew larger and larger arrays to make room for new items. There's one bad thing, and I mentioned it when I was writing this. That trick of adding just 1 to the capacity ends up being a terrible idea for building a resizable array. You could end up spending most of your time just copying over the array every time you have to make it a little bit bigger. On a tiny little input like this 25 element input, You might not notice that, but that's why I made a bigger input, long input. And I think this has somewhere in the neighborhood of 40,000 numbers. And here, if you watch when I run it, you can see it takes a little bit of time, really just a couple of seconds, but that's all the time that we're wasting growing that array just a tiny bit every time and copying everything over every time we do that. And the way I've done it here, it ends up being an n-squared algorithm for 25 inputs. That's maybe not a big deal, but for 40,000 inputs, even on a modern machine, that's starting to slow things down. I wanted to make a few changes to this program. I'm going to say it's working. If you were following along in the slides, this is pretty much what we just wrote. So if you wanted to go back and take a look at it, also the example programs we're playing with right now should be posted on our Moodle page. I want to, in the time we have left, I want to try to improve this program, and we'll do it a couple of different ways. I guess I would say resizable arrays. Those are going to be one of our most commonly used data structures. So we'd like it to be really easy to write code for a resizable array, and I think we can refine this code. I think we can simplify it a little bit, which could pay off if we end up having to write code like this frequently. We can get it down a little bit shorter than what we have. So I'm going to take the same source file we were just playing with, and I want to make a couple of refinements to this little bit of code that we just wrote. The first thing I want to do is what you probably were already thinking. Let's, instead of just increasing the capacity by 1 every time, let's do the usual trick of doubling capacity. So this is going to make our code a lot faster. On that 40,000 input, I don't think you'll even notice it taking any time now. The next thing is, well, this line here where I'm copying everything over, I could make that code a little bit shorter. And I mentioned I had to write my own for loop to do that, but there is a handy function that's part of the standard library that'll do that for you if you know how to call it. And it's called memcopy. So it's got a short cryptic name like most of these C functions. Memcopy is kind of like string copy. It'll copy, except it doesn't care about null terminators, it'll copy any chunk of memory from a source to destination. You just have to tell it where the source is, you have to tell it where the destination address is, and you have to tell it how much to copy. So instead of writing our own loop to copy this array over, we should be able to get memcopy to do that. Let's give it the destination. Will be the new list that we just allocated. The source will be the old list that we already had. And then I think the only thing left we need is how much to copy. Well, our source list is an array of ints. We know that len is the number of things on the list. So it seems like I just need to copy how many bytes, well, whatever size of an int, times the number of things on your list. And this should, so I saved myself maybe one line of code here instead of having to write my own loop to copy the old list over to the new one. I can get the runtime library to do that for me. And it might even do it a little bit faster. I assume that memcopy, whoever wrote the code for memcopy, they thought about it and tried to make that function as efficient as possible. Let's recompile. I apologize. I often make this mistake. And I even thought about it when I started writing this code. That memcopy function is not in standard lib, it's in string.h. So if I want to use it, I'm going to need to include string.h, and then that should get it to compile. All right, let's give that another try. All right, compiled cleanly this time. And let's go back and run it with that 40,000 element input. It still takes a moment to print out the results, but here you can see there wasn't any hesitation at the start. That trick of doubling the size of the array every time really pays off in performance. We are just about out of time. If you're following along in the slides, we talked through resizable arrays, we implemented this version of the solution ourselves, and then we went back and learned about this memcopy function, and that let us reduce the code a little bit more. We are going to learn about other ways to make this even easier. So we'll get our resizable array code down to just 1 or 2 lines of code, but that'll have to wait for next time. I appreciate your attention. I hope that I'm not speaking to an empty room. I'll go ahead and stop the recording, and if anyone wants to hang around and ask questions, we can do that after class.